So the next topic we're going to discuss will be yet another terminal operation in streams, and this is the reduce operation. And as we'll see, reduce is also a very powerful operation that is used to take the contents of a stream and then reduce it to a single result. And once again, we'll show the Hamlet program to illustrate this. So the reduce operation typically returns a primitive value or something that's equivalent to a primitive value, like, capital long or capital integer versus lowercase long or lowercase int. So you'll typically get back something that's a primitive or something that's like a primitive. And we're going to demonstrate this in the context of our Hamlet program once again. And in this case, we're going to create a map, as we saw before, which will have this map of character names and their lengths. And then what we're going to do is we're going to write a little snippet of Java Streams code that will use reduce, and it will take the characters map, the matching characters map that we just built, and it will figure out the sum of the name lengths. So it's going to go through all the characters in the map, and it will sum their name lengths together to give you a final result, which will be the sum of name lengths. And here's how we're going to do it. We're going to take the matching characters map, and we're first going to say, give me all the values, please. So .values is a method on map that will return essentially a set, or I guess it's a list, that is a list of the values. So we'll get a list of longs, which are the character lengths, character name lengths. And then we're going to convert that list of values into a stream of longs. So now we have a stream of longs. And then what we're going to do is we're going to apply the reduce terminal operator in order to sum up the lengths of all the character names in Hamlet. And here's what we're going to do. As you can see here, we pass in a 0 as the first parameter, 0L, because it's a long 0, not an int 0. And 0 here plays the role of something called the identity. And the identity is sort of two things. It's the initial value of the reduction, so we start with initial value of 0, and it's also the default result if there are no elements in the stream. So if for some reason we had no characters at all, we get a 0 back, which would be the right result. The second parameter that's passed to reduce is a method reference that plays the role of an accumulator. And an accumulator is just a stateless function that combines two values into a single reduced value, which is immutable, meaning it's not expected to have any side effects. Once it's assigned, it's expected to stay with that value. And so what we're doing basically is we're going through and kind of pairwise summing all the elements until we end up with a single result. So think of it sort of as a tree of reductions that get done until we end up with a final result, which is the result of summing all the character names together. You could also use a lambda expression instead of a method reference. Here's the way of doing it with a method reference, which I kind of like because I think it's a little bit more readable. But you could also write it like this. You could say open paren x comma y, close paren arrow x plus y. That would also work as well. There's another version of reduce which takes 3 parameters. You can see the one that we showed before took 2 parameters. There's a 3-parameter version of reduce, which is commonly called the map reduce version of reduce, which is most effective when used with parallel streams, which does kind of map reduce, which is a very famous paradigm of parallel computing for embarrassingly parallel problems. And so what's happening here is we're going to start out with the list of characters in Hamlet, and then we're going to take that list and we're going to create the corresponding character list. So we have a list of these things. And then we're going to convert the list into a parallel stream. And then we're going to go ahead and do the following. So again, keep in mind what we've got here. We've got a list of character names. We're no longer doing the map stuff we did before where we have a map that has the names and the lengths. We just have a list of names of characters. And then we're going to convert that list into a parallel stream, and then we're going to use the 3-parameter version of reduce. The first value, again, is the initial value 0. That's what we initialize everything to when we're doing addition. And then what we pass here is a lambda expression that plays the role of the map operation. And you can see what it takes is it takes sum, which is the running sum that we're creating here, because we're going to return this as a long, which is initialized to 0, of course. And then we take S, and S in this case is a string that's in the list of character names in Hamlet. And we're going to create the result of sum plus S.length. So this computation will return a value, which will be the length of the current string we're looking at, plus the sum. So we're kind of accumulating it as we go. And that will be done in the map operation. So all those things will go in parallel. And then we take all those partial results and we sum them together. So that's the reduce operation. So we create a bunch of intermediate operations here, and then we sum those operations together, creating a single final reduced operation. And there's also, by the way, just as a side note here, I think I might talk about this. In fact, I talk about this on the next slide. There's also a sum method that can do this reduce without having to do reduce. It's a little bit more concise. So let's take a look at this. This actually is important because you can use this, or you need to use this for assignment 1A. So in this case, now we're back to our map example, not our list of string example. So we've got a map of character names to lengths. We convert that into a list of values. We turn it into a stream of values. We then convert the stream of values into long primitives. So this is a stream of longs with a capital L. Those are reference types in Java. That's the boxed type, as it were. And then we use the map to long method to convert each long with capital L, which is a reference type, into a long with a lowercase l. And this is a good example of why Java's naming conventions is a little confusing, because it looks like map to long will map to uppercase L long, but in fact what it's really doing here is it's mapping uppercase L long to lowercase l long. Remember, uppercase long is an object, lowercase long is actually a primitive value. So we end up with a stream of primitive longs, and then we go ahead and say sum these up. So that will sum up all the long primitives into a single result. And you can do that in lieu of doing the reduce operation. So it's arguably a little bit more concise. Of course, you have to understand how to do map to long. That is why, by the way, in your assignment 1A, you'll end up using map to int to be able to get the results in int primitive form, so you can then sum them together. There's yet another way to do this. You could use collect, although it's a little bit more off the beaten track, but you can do it. And in this case, what we're going to do is we're going to use values and streams before. So we have a stream of capital L longs. And then we collect those things together using collect. And we apply the summing long collector, which will basically return a collector that produces a sum of the long value function applied to the input elements. So it'll apply long : long value, which takes each capital L long object, it's a reference object, and turns it into a lowercase l long value. It's a primitive long, and then it sums those things up and it returns it as a long. So that's yet another way to do things. My preference for this is probably this approach with sum, because I think it's more clear at a glance what's going on, even though you have to do the map to long conversion. Collect is okay as well, just maybe a little bit more confusing for returning a single primitive type. You can also use reduce on non-primitive values, which at first glance seems a little bit wonky, and it is a little bit wonky, but you can do it. So here's an example that comes from the EX17 folder in my GitHub repository. And you can see here, this is called stream reduce concat. And what it does is you give it a stream, which is a bunch of words, and it goes ahead and makes a stream of this stuff. And we'll talk in a second about what the parallel Boolean means here. And what reduce is going to do here is it's going to create a new string as the initial value. So we have an empty string as the initial value. And then the accumulator is going to basically concatenate each pair of strings in the stream together, eventually ending up with a concatenation of the entire stream of strings. So the plus sign, when applied to strings, concatenates y at the end of x. Okay, so it works. However, it's inefficient because string concatenation in Java will end up copying strings. So when you concatenate two strings together, it basically creates a new string which copies the contents of both of the strings. So it doesn't do in-place string manipulations. It creates a new one, and so that can become very expensive. We'll talk more about this when we talk about the internals of Java streams and combining results and so on. You'll see there are better ways to do this. But it's possible to use reduce on non-primitive types, although it's usually not very advisable. So that's the end of the overview of the reduce terminal operation.